Right, is my screen in full screen or no?
No, you're looking at the
Yep, okay.
in the actual application.
Yep, switch screen. Quick. Sorry about that, and this is why I took it over.
There you go. You're in.
You can see it? You can see it now like that?
Good. It went back.
Yep, no, I'll go right from it then. All right, good. You can see it now?
Yep.
All right, cool. Thank you. All right, so just a little bit about us. Shannon did a good job of explaining who we are, what we do. There's four main processes we do here at Eck, all under one roof, and that's plastic injection molding, thermoforming, fabrication, and assembly. We are celebrating our 75th anniversary this year, and we are a small business. We have multiple processes under one roof, and that's kind of our selling point. That's one of our advantages, that you don't typically find injection molders that will also do assembly, fabrication, all under one roof. So the goal of today is to kind of teach how to source custom plastic parts on our end, just information to share with you. So I'm going to kick off the presentation and send it over to Brett, and he's going to kind of go through the technical steps that we go through, things we see, best practices, and we'll take some questions at the end. Brett, all you.
Great. So, what's the goal here? Right? I mean, the goal is to develop and produce your part so that it works as intended in the most cost-effective way. Put that there in that order because it's got to work. And then, of course, you got to keep the cost down. And there's a lot of different ways to process plastics, so we'll get into that. Things you want to consider, like right off the gate, and we get going, things that we're going to talk about. So, I mean, you're obviously going to have a part design. You want to start to look at material selection. There's got to be probably 10,000 different polymers. I mean, there's a dozen base ones. There's a bunch of engineer grade ones. They fill them with all kinds of fillers and all kinds of additives. You can make them UV resistive to UV light. You can make them so that they actually have lubricant in them. You can put glass in it to make it stronger. You can put carbon in it to make it conduct electricity. There's all these different things you can do. So the idea is there material out there that can help you first? You want to look at that. And then you want to look at the manufacturing process. So you want to take your part and you want to figure out what are the different ways that it can be manufactured. And then what you want to do is take your design and you want to optimize it so that it meets that manufacturing process, right? Because I think if you flip onto the next one, or actually, so you can have it injection molding, you can have it vacuum formed, you can have it roto molded, you can do all these different ways to have it done. So, and then what you really want to do is, in evaluating which process, you want to figure out which one's going to be the most cost effective. So, or actually, I'm going backwards. I'm sorry. Not used to presenting. I haven't done much of this. In picking out the material, you want to basically, if you talk to a material supplier, and we introduce customers to material suppliers all the time because they staff application engineers. So there might be lots of materials that meet the criteria of what you need to do. But a lot of them will end up being overkill. You want to get basically the lowest price one, right? You want to keep the cost down. So you want to look at all the mechanical properties, and you want to think about the environment that's going to operate in, right? So is it going to be able to withstand that operate? I mean, I've been in conference calls with application engineers before, and it was actually a consumer product they were looking at, and they're like, okay, well, is that going to come in touch with sunscreen? The sunscreen was actually really bad for a lot of plastics. So it's these things that you just don't necessarily think of, but you want to look at things like tensile strength, the operating temperature, what it comes in contact with, all these different things that come into consideration. So from there, you just want to make sure it's not overperforming, right? And then I was jumping ahead before. So once you have a material, you then want to figure out the most economical process, right? So we're going to evaluate the various manufacturing methods. Injection molding, blow molding, rotational molding, 3D printing, all these different ways it can be made. And then, so you want to select those processes that are capable, and then from there determine which ones is going to be the most cost effective, because you want to weigh the cost of the production part versus any upfront costs or capital expenditures that you have to put out there in order to have them made that way. And so, for example, you could have them machined. So if you had this part here machined, oh no, it's blurring it. Okay, if you had a part machined where it all has to be cored out and all these different ribs, it's a lot of hours on a CNC. You're paying for that. That's actually the most expensive thing we all deal with is time. So, or you could have them injection molded, which means you get one every 30 seconds, but you have an upfront cost. You have to buy the mold. When you have them CNC machined, they don't have to be, there's no tooling costs involved. So it's weighing that, right? How many of these parts do I have to purchase over the life of the, whatever amortized period I'm looking at? And does that create cost savings enough to justify the tooling? So those are the kind of things that we often help with as well. So what is injection molding? So injection molding, what we do is we take a thermoset resin. So that means that it's put into a plasticized or a semi-liquid state by using heat and pressure. And it travels down. You'll see there's like a screw there. So basically it goes into the plastic granules, go into the hopper. It drops down in. It's moved forward in that screw. That screw moves forward and backwards. Now that little blue check valve, that actually moves forward and backwards too. So when it's pushing forward, it moves backwards against the screw and it seals. When it's pulling backwards to pick up a shot, the material flows in front of it. So in the beginning, it moves backwards. Material flows under that check ring into the front where you see the pink, the molten plastic. And then when it's time to deliver the dose, it shoves that whole screw forward and it injects it in there. Now, the reason why they use that process of actually doing that instead of using the auger to deliver it slowly is because that's how you deliver a lot of pressure. We're shoving the material into these cavities, and a lot of times it takes up to 1800 PSI. And we're not going to get that from the auger, especially with control. So once the dose has been delivered, you see there's a fixed platen, a moving platen, and a mold clamping cylinder. Well, that moving platen will then, once it's been solidified in there, it moves backwards, and then it'll actually eject the parts out of there. So you move on. So the three main components to injection molding. So it's the resin. Talked about that. You want to make sure you pick the resin that works, and it's the most cost-effective one. Also, then the big focus then is part design. We're going to talk a lot about that in the next, or the majority of this presentation. And then the mold itself. And I figured I'd throw out a picture out there because if you talk to anybody about injection molds, they're not cheap. They run anywhere from $8,000 all the way up to hundreds of thousands of dollars. Well, there's a lot of moving components in these. And they have to be able to make repeatable parts over and over again. And a lot of these things are made to cycle often millions of times. Doesn't mean you have to buy a million parts out of them. There's a lot of cost savings to take out of there. So again, that's that big jump from a $14,000 tool to a $500,000 tool. There's a lot of things to take into consideration. But we're basically having these things made so that they are custom built manufacturing of one, and there's a lot of hours and a lot of steps that are linear. They can't be basically stacked on top of each other. They have to be done sequentially. It adds a lot of time, a lot of costs associated with it. All right, so design considerations, injection molded parts. This here's actually, these are parts that we made here. A customer of ours needed a hook. So it was that hook, basically the one on the left, was essentially a prototype. They want to know if it would fit. They want to know if it works. So what we did was we machined it. We just cut it out of raw stock. So that we didn't have to buy a tool. They spent a lot more on that hook than they do on the green one. But at the same time, they basically are able to test for form and fit and kind of for function, right? It's not going to perform exactly the same as a molded part. But the big takeaway here is that you'll see the one on the right, it's missing a lot more material. It's completely cored out. That is done on purpose, and we're going to get into that here shortly. But on the right-hand side is the injection molded part that came afterwards. So through this, when we're talking about part design, we have main considerations when we're talking about the part design. The biggest takeaway from all this, I'm going to say in the beginning, I'm going to say it throughout the process, is throughout this presentation, is to get a molder involved early, because that's going to save you a lot of time and money later. Because there's a lot of things and a lot of tricks that can be done to help you really get the part to do what you want it to do, look the way you want it to look, and yet take a lot of costs out early and also get you to market faster. So the main considerations when you're designing a part is, first of all, is the tolerances. That goes into the material you pick out. That goes into how the tool is built. It goes into if you can even do it or not. Draft is enormous. All parts have to have draft. Coring and wall thickness. That's kind of what we talked about when you looked at the white to the green part. So we shell these things and thin them right out. And then there's also things like corner designs, thickness transitions, ribs, rib thickness, bosses. These are all things we're going to get into. And then how are we doing on time? We're doing good? Okay. This is where we get a little bit more in the weeds. So when we're looking to design a part, we basically want to make sure that we can fill the mold cavity without damaging the resin, right? Again, we're using a lot of pressure, and we're using that heat and pressure to keep the material plasticized that's moving through the mold. But at the same time, we don't want to use so much heat and pressure that we destroy the resin, and it's not going to be, if you want it to be nylon, it won't be nylon at the end. You can actually burn it up and carbon it up. We also have to be able to, once we get the part, once it's been solidified in the tool, we have to be able to eject it, right? And then the other piece of it too is we want to make sure once we eject it, it mitigates warp and it meets all the required geometric tolerances. All that stuff goes into the design. So again, you want to get us involved early because it makes a huge difference. So basically just going to kick off on tolerances, because what happens is that's going to play a lot into your material selection. All right. Because not all materials can be molded at the same tolerance. It actually, the tolerances we can hit come from the manufacturer of the resin. They themselves have tolerances in, when they're mixing their batches, so they're not going to perform exactly the same. On top of that too, we are always fighting shrink rates. Shrink in many materials, the rate of shrink is different in flow of material or transverse of material when it's going through the mold. Then on top of that too, there's also just controlling the temperatures inside the tool. So with all that being said, when there's all sorts of tables online. There's actually a lot of these slides are right off our website and it's on there. So when designing, when you're looking right in the beginning, it's tough to have parts that are line to line. Tolerances go into everything because you're dealing with tolerance stacks right off the get-go. So basically, they're going to vary from material to material, and you'll see things like polypropylene, which isn't on here. It's like the shrink rate's anywhere from 2% to 8%. That's going to play very heavily into tolerancing, whereas a glass-filled nylon is going to be much tighter, or a glass-filled ABS will be much tighter tolerances. So, draft. All plastic parts need draft. So all the stuff that you hold on to, that you pick up, consumer products, your keyboards, everything, you'll see that there's almost never a straight vertical wall that is perpendicular to the parting line, if you can find the parting line on there. So the way I always talk about this is I always describe it as like muffin tins, right? So essentially, if you take muffins, if you're done baking them, draft is where they taper like this. You can see it like the top two pictures there, the one on the right. That's adding draft. Well, because we do that, when you flip the muffin tin over, they all fall out. It's kind of a wonderful thing. If those walls were straight, if they're completely vertical, well, you'd probably still get them out, but you're going to have to beat the heck out of the tin to get them out. You're going to pound on it. It's not good for the mold. It's not good for the parts. It's not good for anything. So if you flip that draft so it's upside down, that's called a die lock. That means we can't get the part out of the mold, all right? It means that we would impale it with the ejector pins before we even end up getting it to come out. We have to dig it out, and it'd be it'd be done. The other thing too, when there's no draft, I mean, the walls are gonna, at best, they're gonna scuff. But again, you can eject. We'll end up impaling it with ejector pins. They all have to have draft. And draft can be material specific and texture specific. It can be half a degree, or it can be, sometimes it needs to be a couple degrees of. All right. So moving on. So coring and wall thickness. This is a big one. So in molded parts, you don't want to shoot big hunks of plastic into a tool for a couple of reasons. This goes back to the previous thing we're talking about before. So when you're machining a part, it's a lot of time. You're paying for that time. Well, the thing that drives the cycle time in an injection molded part, above all, is the wall thickness. So when we inject, so basically we'll inject, that takes a couple seconds. We'll hold it until the gate freezes off. So the material, when we stop injecting and we let off, the machine lets off the mold, the material doesn't come back through. Right? We want to make sure it stays nice and packed. So that only takes about 10 seconds. And then we hold it for as long as it takes for that part to solidify and be stable in the tool. And that can take, that right there usually can take 15, 20 seconds. It by far takes the longest. Now, plastics inherently are great insulators. So that means if we were to put a ball in there, well, basically, if we leave it in there for 30 seconds, we're going to be dropping a tomato. It's going to splat. It's not going to hold its shape. So you want to have thin wall thicknesses. You want to basically core them specifically to, one, reduce cycle time, which saves piece price. On top of that, too, and we're going to get into it later, but it also mitigates warp and it helps with tolerancing. And it also, because if you have a thick part, another thing that happens too is it's going to be full of voids. The resin, as it's traveling through the mold, it actually sticks to the sides and it kind of rolls out. So the middle's kind of rolling out, like if you ever watch lava, the middle's coming out, it's flowing forward, and it's kind of going out and sticking to the walls, and it's kind of freezing off as it hits the walls of the cavity. So, well, what happens is that it's going to, if it's too thick, it's going to gobble up some of the air that we're displacing in the mold. So if you look around at anything after this, you'll see that you'll never find parts that have like half-inch thickness that weren't machined, or at least that were injection molded anyways. It's just really, it leads to all kinds of problems in the molding, in molding. And wall thickness is, you'll see on that past screen, I'm sorry, it is actually material specific. So there are materials that can go to extremely thin walls, like 40 thousandths or even sometimes 20 thousandths, and there's some that you can actually have thicker. All that's based on the viscosity of the melt flow. Again, I'm touching at a high level on a ton of this stuff. The best thing you can do is get us involved early. But when you're designing, coring wall thickness is big. Corner design. So when you're designing a part, if you're working in CAD, the best thing you do is you draw the part that you want and make it solid and thick, and then shell it, because that's how you'll end up getting to the third part, the third section, the third picture there. Because what you'll end up happening is, on the left-hand side, it says it's too thin. Well, you have a weak corner, and then B, on top of that, when you're flowing, you want to maintain consistency of melt flow. So from there, you're going from thick to thin to thick. And that's not good for the melt flow, and it actually, again, messes with tolerances. And it just, yeah, it messes with tolerances, it messes with warp, and it basically, you end up with a part that's not really kind of what you're hoping for. In the second picture, too thick, again, you're going from thin to thick to thin. In that scenario, it's not quite as bad, but it's, as far as the melt flow, but at the same time, it's horrible for cooling, because what's going to happen is that thick section is going to cool. It's going to take longer to cool that corner than it is the walls. So it's going to build molded in stress, and it's going to cause warp. That consistent wall thickness, you have even melt flow, you have even cooling. Those lead to better tolerancing, reduced warp. It's just, it's a better design. Then basically thickness transitions. So those last two, basically you can see it's kind of gradual, is what you're basically looking for. You want it to hit and then basically slowly reduce. You don't want a hard because when it touches, if you go to the left where it says incorrect, it's going to freeze off on that wall, that step. You also have inside knife edge corners. Those right there are just weak, right? You always want to put a radius there. It's a much stronger geometric shape. So you want that basically to hit and then kind of force all that material to go back through the thinner section. So basically we're immediately jump into, breaking rules. Your parts are going to break rules. You're never going to find one that basically meets all these and it's absolutely perfect. But the idea is that you start those conversations early in what's the most important aspects of this part, and we'll work with you to ensure that those are incorporated in the part design. So, ribs. So in here, there's actually two things going on, and I'm actually going to show that. But basically, when you core something, you take the material out, and you may have wanted it there for spacing because maybe it's a fixture and hold something in place. Maybe you had it there for strength. Well, back to that green hook. That green hook, those ribs add a tremendous amount of strength, right? Basically, they end up adding like bracing between those thin walls. And then on top of that as well, it also gives them the thickness that they're looking for as far as any kind of, holding things in place where it needs to be. So whenever you're designing a rib, you want the rib to be 60% of the adjoining wall thickness. You can't forget the draft. That's also huge on that. It's also huge. And then the other thing that happens as well is sink. So sink, if that wall thickness is at the bottom, yeah, Sean, if you point to that, yeah, right in there, that's dipping down in there because there's a lot more material there. So let's say if everything shrinks at 1%, well, the distance from the middle of that part to where that is greater than the distance of the wall thickness. So when it basically shrinks back down, then it's going to sink in that place because it's shrinking to basically the same percentage. So it's just going to leave that mark there. Again, boulders are happy to allow that to be there, but again, you can design around that if that's something that cosmetically is not okay. All right, so moving on. And then rib thickness. So I guess I apologize, I jumped ahead before. With the ribs, you want them to be 60% of the wall thickness. That's huge. That's how you avoid sink. And that also helps with ejecting the part as well, surprisingly enough. But it's, again, making sure you have radiuses in there and not hard corners. You got to have draft like we talked about before. And then you just, again, want to make sure that 60% of the wall thickness. It really goes a long ways to avoiding warp with your parts. All right. So this here, so again, it goes back to, these are kind of like tips and tricks. So bosses, so when you have a boss, so if you look down in the picture on the right-hand side, right, they have the incorrect and the correct. So the incorrect's on the top. So you can see the way that those are attached to the sidewalls creates thick sections. Again, those are going to be sinks. The sinks, they take longer to cool. So basically, after you eject the part, they're still going to continue to cool. And they're going to pull the other walls in. It's going to cause the parts to warp. And then when they warp, they're out of tolerance. So when you look at the picture below, things they did is they actually have a rib connecting the boss. The rib, 60% of the wall thickness of the boss and the adjoining wall. Right? So basically, you're still following those same rules. The bosses themselves, so if the boss, and then you have to have draft on the bosses. Well, that causes issues, as you can see in the picture in the top left, because you actually end up with those thick sections. A couple ways to mitigate that. The hole that goes down in, you put them deeper, because that right there minimizes the amount of material there that's in that corner. Another way you can do it too, the picture on the right, you can have a moat. The moat can go around it because that also minimizes the wall thickness. Those are things that can be done because sometimes that boss has got to be kind of long. If you have draft on it, that means the bottom is a little thicker than it should be. So you can do these little tricks to kind of mitigate it. And those are the kind of things in advance. It's just best really to, again, draw what you're looking for. It's great if it comes to us shelled already. And then from there, we do a design for manufacturing. We can get it back to you. And we'll talk a little bit more of that afterwards. Oh, right here. Perfect. So when we get a new opportunity or a part that's presented to us, what we start working on is our project manager will start working on a design for manufacturing to give feedback on that part, right? So what kind of features in there that will end up being problematic to the molding process, right? So what things can be addressed, and we'll even put in there things that, okay, we can mold this way, but you'll end up seeing this, or we just can't mold it this way, but here's tips to basically mitigate that or get around it. So in that, if the part's complicated, we'll often do a flow analysis so we can know we can fill the part. We can get an idea of what the warp will be, or if there is going to be warp. I mean, there's always warp, but to what degree? And to basically be able to give a good idea of what you can expect once you get your first samples. And then at the same time, we're also working on a quote, because in the beginning, we want to be able to kind of like say, this is a ballpark, what you're looking at for tooling and what you're looking at for your piece price. And if the part is close enough to its final design, I mean, that's going to be incredibly close and maybe even finalized anyways at that point. But we try to present a quote and a design for manufacturing right off the get-go, because it just makes a huge difference to kind of get that conversation started about, you know, how can we make the part a little friendlier to the injection molding process and kind of give expectations of what you'll receive. All right. So then basically you have to buy the mold. So when you, with the quote, you'll end up getting a price for an injection mold, and you're also getting a piece price. All right. So when we're pricing an injection mold, we're taking into consideration really the quality, like the tolerances in the part and the material of the part, because certain materials require certain features in the mold, and then also the quantity. So like we talked about before. So if you had a tool is gonna expect it to produce 10 million parts in 5 years, well, we're gonna spend a lot of money on that mold because it's gonna drive the piece price way down, and that'll drive the total project cost down. So unfortunately, it's a little more to eat up front, but at the same time, it's really going to save you an awful lot of money in the beginning. But at the same time, if you're only going to buy 500 a year, then we can get that mold price down, and it's all part specific and size specific. But you can get that part price down. Mold price down. I mean, we see them as low as $8,000. I mean, I'd say the average mold price is probably around $25,000, or maybe not even. It's around like 20 grand for something that makes 50,000 parts a year. Because we are working to balance those upfront tooling costs with a long-term performance and volume needs. And then we just want to make sure it can handle the material and the process efficiently. I mean, you don't want any headaches. You want everything to show up on time. You want to get exactly what you expect to get, and it meets your needs. And just keep the pricing down. So, and kind of talking a little bit about that. So this has all been about injection molding. We do injection molding and thermoforming. And one of the big parts of thermoforming is vacuum forming. And just idea of kind of just comparing different ways that you can have things done. So if you were to take a part, say, is it going to blur it out? Yeah, it is. Let me see if I can fix that. Nope, I don't think I can. Oh, yeah, I can. No, I can't. Okay. But a lot of times, if you were to mold a part with some real complexity, like if that bucket hook, for example, it was probably like a $30 hook. We only wanted a couple of them. It's a lot of time, and then the material itself is very expensive. That molded hook, I think is like $3. It's actually significantly cheaper. They spend like 20 grand on the tool. So the idea is they buy enough of them to cover the cost of the tool. If we were able to vacuum form that, which we probably could, we've had to change the shape drastically, but we could have figured out a way to vacuum form it. So just comparing it. So if you were to vacuum form, can say for the same part, you have a $5,000 tool versus an injection molded $14,000 tool for a single cavity mold, right? So let's say the time, right, the rate per part. So when you're injection molding, it's about 79 cents per part in just time, because molds opening, they drop, closes, 30 seconds later it opens, closes, drops apart. Rate per part when you're vacuum forming, we first have to put a sheet of material in, it goes into like an oven, it heats for a couple minutes, it comes out, a mold comes up through it, it sucks the material down around the mold. That takes about 30 seconds. And then it has to solidify for 2 minutes, for another minute. And then we have to have the part come out. And then we have to go ahead and we have to put it on a 5-axis machine and we have to cut that thing out to its net shape. So you're looking at like 5 minutes apart versus 30 seconds apart. So machines have similar run rates, but you can see it costs a lot more per part. Then the material cost per unit, well, the resin itself often is much cheaper. So say the part is 95 cents for the resin, the total piece price of $1.74. Well, the extruder that we bought the sheets from when we're vacuum forming, they had to buy the resin, and then they had to extrude it. So, and then on top of that, we have to cut it to a blank size, a proper blank size. So it just drives the costs up before you actually have the net raw material you can work with before you even start to mold. So you're looking at $10.78 piece price for a single cavity, all things aside, and then for the molded parts, $1.74. So there's setups in both of those. So the setup, if it costs $100 to set up an injection mold and it costs $100 to vacuum form, well, if you buy 100 parts, you're looking at, so you go to the next part, the piece price, including the tooling. So that's what this does. This next table, it takes that injection molded part and it divides it by the annual quantity. So, and it adds that to the piece price. So we have $1.41 per part for 100 of them. And that's just in the first year. But for 20,000, it's $2.44. If you look over on the right-hand side, for 100 of them, it's $60 a part with the tooling. And that's in the first year. Then your tool's paid for. And then after that, you're back. It's basically, you're only paying $10.78. This is just accounting in the background to kind of figure out your project cost, right? For 20,000, you're looking at $11.03, right? So then you go ahead and you put that on the annual basis. So if you're buying 100 parts, well, then you're looking at $6,000 for vacuum forming plus the tool, right? So injection molded for 100 parts, you're looking at $14,000. That's your tooling. So basically, it's $174 in parts and $14,000 in tooling. It's expensive. The tooling's the expensive part. But if you end up buying 20,000 that first year, you only end up spending just shy of $49,000. If you're buying 20,000 vacuum forming, you're paying all that in the piece price over and over and over again, and it's $222,000. Then what this also shows, you go further out, the columns in each table is the cavitation. So what you can do is instead of dropping one part at a time, you can drop 2 or 4 or 16 or 32. When you're looking at bottle caps that go on a Poland Spring bottle, I think because a lot of the molders use that, or a lot of tooling manufacturers use examples. It's like a 2-second cycle, 96 cavities, probably cost, Poland Spring $650,000 for that tool. But it probably takes 1,000 of them before they get to a penny. They just drive that price down so far because it's running so fast. And that's the point. That's the name of the game, right? And then again, if we were paying, even though there's no tooling, if you had a machine, you spent $20 a part. That right there, that's great for prototyping. That's great for very low runs. But again, as you invest in tooling, they'll kind of start to save you money as your volumes go up. And it's surprising how quickly you can amortize the cost of a mold. 500 parts, and that's in the first year. Most people amortize their tooling over 2.5 years because you're going to depreciate it on your balance sheet over 5 years. So a lot of people, to get a return on equity, you figure you go 2.5 years so that you're basically doubling your return on the tool over the time that you are writing it off through your taxes, if that makes sense. So 2.5 years, it cuts that tooling cost even in half per the piece price. All right. So moving on. So big things to get the cost down when looking at molded parts. So when we're building, we have all the tooling sourced. I'd say 90% is done overseas in Asia. There's a lot of amazing molding builders over there, and there's a lot of bad ones. We have relationships that are 25 years deep, actually longer than that, like 35 years deep, where our project manager's been over there. We know them. They know their kids. I mean, we have extremely strong relationships with them. All they really want to do for us is build us a tool. They're happy to mold parts as well for bridge. It's more expensive usually to do it that way. But we have a lot of phenomenal mold builders over there. The world's done an excellent job of training Asia how to do it. And it's because the mass production of one. There's a lot of time that goes into the engineering and the design of these things right up front. So that's one way to really drive those costs down. Colorant. So black and natural colors are always the lowest cost. So internal parts, it's great if it could be one of those two. But of course, branding is very important. You can't add color into anything. It just adds to the cost. Family tools or mud molds. So a family tool is, so say if you have two parts that are always going to be bought together, it doesn't always work, but if they're similar in size, we can put two parts in one mold so it drops them at the same time. It's like everything else in life, balance is key. So you really want them to be similar size and you want to be bought in the same quantities. Because if we're always working on one cavity, it actually is not good for the ejection system and other parts of the tool as well. So you kind of want to make sure that they're running together. And then mud molds. So we can buy essentially just cavities injector systems that slide into a utility or universal mold base. So that is not a great practice when there's any kind of volume behind it at all, because that adds a lot of risk to the tool being damaged. It's also sacrifices a little bit in the tolerances because these things have to be made to be fit together over and over and over again, instead of having a fully framed mold that's just open and close, and we do some maintenance to it, but it's basically fitted specifically for that cavity. These things are held to incredibly tight tolerances. The molds themselves, the way they fit together, they're held to tenths of thousandths of an inch. Then basically any secondary operations. So, and looking at it, so when you have a part that has an internal thread, I'm just using this as an example. Well, when the mold opens, it's going to be stuck on those threads. So if you have like the bottle cap, well, we go to eject that off, it's going to rip those threads out. So we can either set it up so that it unscrews out of the mold, which is going to add a lot to the mold costs, or that core that's sitting on actually collapses and it gets smaller. So it basically ejects easily. But again, adds a lot to the mold cost. Or if the volume isn't enough to justify that, we can take that near net shape that comes out of the mold. We can machine the tap threads in afterwards. Both of those are incredibly common practices. There's nothing wrong with either one. Again, it goes back to the costs, which are usually driven by the volumes that you're buying. So those secondary operations, how much of it can we have in the tool and how much can we have in the tool? And then tolerances. Tolerances are huge driving and both of that. Basically, when you're designing your part, you really only want to, if you can, tolerance and dimension the critical parts of the geometry and leave the rest just open. We are going to build the mold based on your CAD file. But then we're going to, while we're molding, produce to the print. So what happens is that the geometry that you put into that CAD file is going to end up in the mold. But what ends up happening is, like I mentioned before, all warp comes from uneven cooling. And uneven cooling comes from uneven wall thickness. It comes from direction of flow. It comes on where the gate is located in the mold respective to the end of fill. It has to do with where we place the water lines in the mold. So if the mating parts are toleranced, and we have those, we know what they are, we focus very heavily on them to make sure they land exactly where you need them to be, right? So, but then the other stuff is going to come out looking the way you want it to look, is going to come out performing the way you want to perform, and it's going to be generally in the same geometric shape. And that makes a huge difference. The tolerances really drive an awful lot. Okay, and again, get us involved in that early, because in doing that, we'll start talking about tolerances early, because we also want to make sure that they can be hit. So mold buying process. So in the beginning, we start with your CAD file, your part, right? And we like a CAD file, we like a print. The print really adds a lot. If we don't have a print right away, then we're gonna have a lot of questions about it, but it's open conversation anyway, so it's really pretty simple to work through. But from there, we're going to put together a complementary design for manufacturing, like we discussed before. And we're going to move to a preliminary quote. Typically, that's all done within 3 days. So that comes back to you. So you have pretty good ballpark on cost and kind of what things we can and can't do in the tool, and even some ideas on cost savings. So we work with you to optimize that part design. So then once it's designed, you'd send a purchase order. And then also too, with molds, everybody, they collect half up front, if not the whole thing. We collect half up front for the tooling itself. So, and then we basically get to work. So the mold builder at that point designs the mold based on specifications that we provide them. We have general specifications based on how it best runs in our shop, because we have definitely conventions and a nomenclature that we have to our shops specifically to make sure that it's just easy in and out, and also for maintenance as well. And then we also put in there part-specific ideas as well, things that we want to see, like what surfaces, where the gate can be, where it can't be, where it's okay to put ejector pins, where we'd like to see the parting line be, and also what areas to focus on in the tool. So from there, they design the mold. They move pretty efficiently to that. That's usually done within just a few days. And then when that's done, we get the mold design, we review it, we approve it, and then from there, they get to work building the tool. So that is about 7 weeks from there, because that first part's about 2 weeks. It's about 9 weeks from the time that we receive a purchase order, and we have the final design, receive a purchase order, until you receive your first sample parts off that tool. So we have local mold builders, but at the same time, most of them are done overseas because there's significant cost savings and there's no compromise of quality. But we end up getting a part back, usually within 9 weeks of the time that we have that purchase order and the final design. Those parts go to you for tool approval. So we want to make sure that the tool yields what you want to yield, basically that it works. So we also usually critique them a little bit because we want to make sure that they're ejecting smoothly. I mean, these are things that there's signs that we can see. Make sure that there's no burn marks or anything in it like we talked about before. We want to make sure the tool is properly vented and the material can flow the length that it needs the length. All that's vented, that's almost never an issue. But basically just going through that to make sure that you're approved. That is the tool approval process, because once you approve of what the tool yields, then from there, we end up shipping it. So when we ship by boat. So that comes sea freight, and that takes 7 weeks in itself. So we typically say it's about 14 to 20 weeks to get the mold here and have us doing first trial samples here. And that's to mold for you to approve our manufacturing process. So that comes with first article inspection reports. That comes with samples from each cavity. And in times when necessary, we can also do a PPAP. So that right there is to approve the manufacturing process so that you know that you're going to get consistency from run to run. And it's at that stage that we go ahead and we finalize the drawing, the print. Because you've basically fitted them, you know that it works, and you want to make sure that the tolerancing is where it needs to be, because at that point there could be a couple things that are still maybe a little bit out of tolerance. And again, it's not the main things that you focused on in the beginning, but it's more so if there's other things that, where it needs to be there. The example I always give is kind of like a Bic pen. So you take a Bic pen, right? So the cap itself, so that's the molded part. So let's say it gets here at that point and you put the cap on and you flip the mold and you flip the pen upside down, the cap falls off. That is a critical dimension, and that needs to be corrected. That's corrected before the part even gets here, before the mold even gets here. But at the same time, if the little doohickey that kind of holds it up in your pocket is maybe 1/1000th too long out of tolerance, so it's actually 1/3 longer than a human hair, then to go back and fix the mold and delay the project is really not cost effective in time or dollars for anybody. But changes are included in the tool price as long as they're the main things that we've been talking about all along. If there's a major modification that comes, then those unfortunately are not included in the tool price. Because sometimes something comes in where they say if there's 90 mating parts and one of them actually offsets, kind of domino effect of the tolerance stack, and something has to move and add a whole new feature, that's a rework. But those actually, if it's still in Asia, those are very cost effective. They're not terribly expensive. But basically through that process, that's an engineering approval process, right? So basically the engineer is saying, yep, this does exactly what he wanted to do, and we're going to modify the part in the end. Modify the drawing in the end. Saves everybody money. A quality approval process is where I say, nope, it has to meet the print no matter what. Because that adds a lot of rework steps and a lot of time. So we plan for that in the beginning if it's a quality approval process, and then that drives the piece price, the tooling price up. So, all right, I guess moving on. And that's it. So, yeah, I think we're going to move to questions, but I was a little nervous jumping into it. I just want to say thank you for joining us. And, yeah, we are happy to answer any questions and happy to help with anything you're going on as well.
Thank you, Brett. We've got a couple of questions that have come in through the chat over the course of the presentation, if we want to start with those. The first one is, what is your maximum and minimum order size, and what is your downtime?
Okay, so maximum and minimum order size. There is no minimum and there is no maximum. Basically what we do is for minimums, what you're paying for in the piece price is you get quantity breaks. So let's say it costs $100 an hour on the press. We call it the machine, the injection molding machine press often. So, well, let's say if you have an hour of setup and then it takes all of 30 seconds to get the first part, well, then you have 100 plus your piece price, and we even throw a little bit for purge and yeah, that. Whereas if you end up buying 1,000, well, then that $100 getting advertised over the 1,000, so that's only adding 10 cents to the part. If you're ordering 10,000, well, then it's not even a cent. So there's no minimums. We actually have parts we run 5 a year, because that still is, unfortunately, the best way to make that part. But at the same time, they end up a little bit more expensive part. They get 5 a year, well, then they end up with the $20 a piece part. Whereas if we're, again, it really just falls to pricing. And then if we need 10 million a month, well, then we figure that out in the project in the beginning, and we do one of those things where we have, 16 cavities in the tool so that we're dropping enough to keep up with volume. And then at that point, we've amortized so much of the tooling and so much that startup that is not even a penny in the part, and you're really just looking at piece price. So for maximum minimums, there are none. It's really project specific, and we're happy to help with all of that. As far as downtime, so if you're talking about time between run to run, so from there, we've actually put an awful lot of effort and work into basically, kaizening or taking out the waste. So, we have a lot of these materials need to be dried before they go in. So the drying time can be 4 hours, right? Nylon can be extremely difficult to dry. And, sometimes it can actually take 8 hours. So we actually have extra dryers for staging. We've put specific tooling in for quick connections into ejector systems and to get the mold in and out quickly. And basically, we spend an awful lot of time just working on that process and any applicable tooling or even specific like mobile tool carts to make sure that we're getting those things in and out quickly. So the downtime really is minimal. If you're talking about in the middle of a run, things come up periodically. Sometimes something does go wrong, go right. That's not that often, because part of that process that we have in the beginning where we're working on the process is really also evaluating things that look like they're wearing, looking at the tool, maintenance to make sure that it is not going to go down. There are some molds that are just generally problematic because of features, or they were never meant to make the volume that they're making, but still not cost effective to buy a new one. At the same time, those volumes are, when that happens, those volumes are low enough because you can't justify new tooling that it doesn't cause an issue for the customer. We're able to kind of repair it quickly and move on. It's really not a common thing. So hopefully that answers that part of the question.
All right, I'm gonna move on to the next one just for the sake of time. From Steven, he asked, is it common to start with a machined or 3D printed part for POC and then redesign for molding?
So is POC prototyping? Is that what we're talking about?
Proof of concept.
Proof of concept.
Proof of concept. Thank you, Sean. So yeah, those are actually recommended. You want to be pretty far along before you buy a tool. You can definitely 3D print for form and fit. Function is debatable, depends on the material and what you're using it for. And then machined parts, it's not going to perform exactly the same, but it's going to be a lot closer. The reason why is because some materials have a grain, actually move in specific directions. So if you have even like a glass-filled material, that glass filling is going to move. It's going to be in line with direction of flow. So, and a lot of times we like to design the tools so that we have that glass fiber moving in the direction that you need it to be so that it produces the strength where you need it to be. And those kind of things have taken consideration. So they are definitely places you should start. For function, it's not perfect, but especially machining will be close. Yes, you should definitely go that way. So where are we now? Hopefully that answers the question. And whoever asked the question is welcome to chime in if I didn't fully answer it.
Yeah, absolutely. The next one asks, what are the material utilization rates for the different processes? What happens to manufacturing byproduct, and is it reused as feedstock?
So, utilization. So if there's a good amount of volume, we can justify to put in the tooling, we'll put what's called a hot runner. So in the mold, on the section of the mold where the material's injected in, we put in what's called the hot half or hot runner. It's a heated manifold. That's when the material enters the mold, it actually travels through that mold, and it stays plasticized in there. And it delivers the material directly at the gate. So there's literally the only waste is just a little bit of purge in the beginning. There's no screws, there's no running, there's nothing that's coming out. Often there is a cold runner, which means that the material travels through the mold to get to the part, and that solidifies in the mold with the part. So when that happens, those end up dropping out. So your sprues and runners are usually about 10 grams of material. That can vary for parts that get exponentially bigger, but for the most part, they're usually about 10 grams. So the percentage utilization is really respected to the size of the part, because the part can end up being just like this little tiny cap that really the runner itself is bigger. In that case, we try to actually add cavitation because surprisingly enough, in Asia, the tooling price usually has a lot to do more so with the mold size than it does the complexity of the part. So with that being said, you can usually add a lot of cavities to mitigate that. So unfortunately, that is part of it. Most of the time, those screws and runners are recycled. But what happens though is that these things are very recyclable. They do go to recyclers. So what they end up doing, the recyclers, they take the material, they grind it so it gets back into a regranular, and they can sell those, which isn't always great. Most molders don't want that stuff, but they can run it. Depends on what they're running. What they do is they'll send it to a reprocessor who puts the plasticizers back in, because in the resin, they add stuff that allows it to flow through, or to basically manage the molding process, the stress we put to it without damaging the material. So it's much better when they put those replasticizers in it. But the reason why that stuff is way better than, say, the stuff you put in recycling bin is because they know exactly what it is. Polypropylene is not just polypropylene. It is a grade of polypropylene. And to know what that came from, it's very difficult on the back end for them to understand. They know the grade and specifically what it is when it's coming from us. So that goes to recyclers. We can ourselves. It is acceptable to grind, is an industry standard, to have we can have a grinder, and we actually have a grinder. We can have those screws and runners going into a grinder and automatically conveyed back up into the feed throw of the machine at a very specific rate of 20%. Because 20% regrind and 80% virgin material is very widely accepted and is really not, that wouldn't degrade the material. The plasticizers mix back in there, it works really well, it injects through. The jobs that we have here that justify the volume of keeping the grinder clean, because again, I have to worry about cross-contamination between job to job. The prints require virgin material only. So we don't do it, unfortunately. But again, those screws and runners are going to a recycler who sells it to someone who sells those granulars to a reprocessor, and it does get recycled. There is very little material where the recycle that we have that we just run so little that we just throw it away, because again, they want to buy in volume, and I can't. They don't want 15 pounds of a random material they can't mix in with something else. So as far as the waste goes and where it ends up going, we're pretty good about that. We're not great about putting it back in. We'd like to be better about that, but unfortunately, the jobs we run, we don't dictate that.
I just want to reiterate. Sorry, I just want to reiterate what Brett said. We can only use the material we're directed to use by our customers. So as a customer of ours, if you put on the print what material to use, if you allow regrind, we're able to use it. If not, we have to use what is specified on the print.
All right. Well, we are over on our time. We do have one more. I feel like maybe this could be a really quick yes or no. But
Yeah.
can I do two-shot injection molding where a part can be made with two different plastic materials?
So I do not have a machine that does two-shot injection molding. So what I do though is we do an awful lot of overmolding. So we mold one part, then we put it into another cavity in the same press, and then we'll actually injecting over it to get that second part, and to get the completed part. The two-shot is more efficient. I have many times over, you find a project that justifies it, buy a machine. If the project justifies it, I'm happy to buy a two-shot machine. And because it's really not much different than what we're doing here, it just has the ability to do it. So we're ability to process it out. We have the ability to process it out. And at the same time, if it's a smaller volume, then the overmolding often can save you a lot of tooling costs anyways.
Great. Well, Brett and Sean, thank you so much. This was super informative. And I know I learned a lot of different things today that I had no idea about. But thank you guys so much. Again, we so appreciate it. If anyone has any other questions for Sean or for Brett about Eck, feel free to shoot them over to me, and I can get them over to them as well. But thank you all for joining us. Look out for information on next month's webinar. It's going to be on intellectual property. We're going to have an IP lawyer on with us. So yeah, thank you so much, and we will see you next time.
Thanks for having us.
You.